guys, welcome back to our robotics training sessions. In our previous session, we discussed continuous time machines. To be precise, we programmed a robot to follow this black line on a white tile. We used a continuous time principle. What we mean by continuous time is that unlike the previous two examples where we had a finite state machine for a two-state FSM, in that example, our robot was limited to just two sets of actions, either moving forward or moving backwards at that constant speed of 30. However, for the continuous time machine, we saw that there was no specific action and that the robot's action at any point in time was dependent on a mathematical equation we derived. Let's have a quick recap. So, we first of all measured how much reflection our light sensor obtained from the white surface. And if we would remember, on the white surface, our robot recorded 78% reflection, and on the black surface, it recorded 16% reflection. So, we needed a way to position our robot, and we agreed on an initial position or a preferred position of half of the sensor pointed to the black line and exactly half pointed to the white surface, in which case we are expecting an average of 47% reflection if the robot is well positioned in this preferred state. In continuous time machines, what we want to do, or in automation or in control systems, what we want to do is to design a feedback system where we are able to measure the error or the deviation from our desired or preferred position. So we have to come up with an error formulation. In a way, how can we calculate the error that will occur while the robot navigates? We came up with this formula that the light sensor readings minus 47, because in this desired position, the light sensor will be receiving 47% reflection, which meant that anytime the robot drifts more into the white portion of the tile, the reflection will increase. If the reflection, say, increases to 50, then this formulation becomes 50 minus 47, telling us that there is an error of 3. On the other hand, if the light sensor drifts more into the black, then the reflection value is likely or is going to decrease. Let's say it decreases to 45. Then this formulation was going to give us a 45 minus 47, resulting in minus 2. So we could tell that the error formulation was going to give us a positive or negative value depending on whether the light sensor is drifting into the black line or the white part of the tile. We looked at how this error can be used to control the movement of the vehicle. So we came up with a relationship between the control. So after we detect the error is used to control the actuation. So the actuation we wanted to control was the steering of our vehicle. And we realized that the steering varies as the error, because as the vehicle veers more into the white or the black, the magnitude of the error will increase, requiring that we steer more. And as it drifts less, the value of error will decrease, requiring that we steer less. However, we needed a constant of proportionality, so we could equate error and steering. So we came up with the formula steering is equal to a certain constant of proportionality times the error. And then we programmed this and looked at how this behaves. In this video, I'm going to pick on this and draw your attention to something. Now, our steering is dependent on the error, and our light sensor readings are ranging from 16, which is the least value we could have when the light sensor is totally in the black, and then 78, which is the highest value of reflection we record if the light sensor is drifted totally into the white, which means the maximum error we could record from this formula. The maximum error we can record will be when we have the maximum deviation, which is so let's look at this. The maximum error we can record error max would be when we have our maximum reflection from the light sensor minus 47, and that gives us what? 31. And the minimum error we could record would be when we have the minimum value of reflection from the light sensor minus the 47, which also gives us minus 31. Now, if we are saying that steering varies as error, then it means our steering value or the amount of steering we can apply in controlling this car is limited to minus 31 all the way to positive 31. So our robot is limited in how much steering it can apply. Mind you, this would be the case if our constant of proportionality is set to 1. But you saw that in our first example, we used a constant of proportionality of 0.5, which would even further limit our steering between 15.5 and negative 15.5. What we want to look at in this session is to give more control to our vehicle by altering the values coming from the light sensor. I wouldn't use the word altering, let me say calibrating the values coming from our light sensor. These light sensors have been designed to operate between values of 0 and 100. However, our light sensors are recording values between 78 and 16. So how do we open up this scope, or how do we calibrate or standardize our light sensor so it operates within its standard operating values? And that is what we'll be doing in this session. I hope you are all privy to equations of straight lines. So let's get going. So light sensor calibration. Let us take these two axes. We have taken readings from our light sensor. So let us say this is we are going to plot our light sensor readings against the standard light sensor readings. So if our light sensor were standard, what should we have been recording? We will plot that against what we are actually recording. So, we recorded 16 from our light sensor when we placed the light sensor fully on the black. At that point, according to the principles of science, a black surface was expected to absorb all the light. So, we should have been expecting 0 from the light sensor. When we position the light sensor on the white portion of the mat, we recorded 78. However, if we should have position, or if we look at how the sensor is supposed to behave, then on a white surface, it's supposed to reflect all the light incident on it. So we should have been recording 100. So if I match the behavior of my light sensor to that of a standard light sensor, it means I can have a point here, and then another point here. No, sorry. X, Y. Another point here. So the point 16, 0, and then the point 78, 100. So when we expected 100% reflection, our light sensor recorded 78% reflection. And when we expected 0% reflection, our light sensor recorded 16% reflection. Drawing a straight line through this gives me that with a y-intercept here. Now, if I am able to come up with the equation of this straight line, y standing for the standard light sensor and x standing for, this is the x-axis, this is the y-axis. But in this case, x standing for my light sensor's axis. So it means that if I want the standard values, then I need to find the gradient of this line, so that if I should multiply that gradient with values coming from my light sensor, and I add a C, where C is the y-intercept, where this line touches the y-axis, then I can say that I can use this equation to standardize the values coming from my light sensor. That is, I multiply the light sensor values by a gradient m and then add a C to it. Let's go ahead and find our m. So our m is, as you know, change in y over what? Change in x. So the gradient of this line becomes, let's name our values. So we pick one point as our y, point 1 and another as our point 2. So let's say our point 1. So I'll name y1, x1, y2, x2. So we can say that our gradient will be change in y, which is y1 minus y2 over x1 minus x2. And that should give us our m as 100 minus 0 over, that is 100 for y1 minus 0 for y2 over x1, which is 78, minus what? x2, which is what? 16. So we have our gradient m going to be what? 100 over a 2 here and a 6 here. 100 divided by 62. So our m value gives us 1.613 approximated to m as 1.613. So how do we find our c? Let us fit that equation. So y equals what? mx plus c. If we substitute 0.1, or let's pick 0.2, makes it easier. If we substitute 0.2, when y was 16, x was 0. So we can say 16 is equal to 1.613 times x value at that point, which was 0. Our y value was 0, Our y value was 0. M by the x value, which is what? 16 plus what? A c. So we have 0 to be equal to, if we multiply that, we get 25.808 plus c. This can move to the other side, so we can say c is equal to minus 25.808. So now we have come up with our gradient and our y-intercept. If we had a graph book and we had to plot this, we would not have needed to calculate our c. It would touch the y-axis at that point, negative 25.808. So with this now, we can then say we have an equation or a mathematical equation that can be used to standardize our light sensor. So what we can then say is that from this, it means the standard values to be used by our robots should actually be the light sensor values. So let's use that. So standard values to be used by our light sensor. I did not want to click any of this. Let me use that. So the standard values is equal to the m value, which is 1.613 times the light sensor values minus 25.808. In what we mean is that instead of using the raw light sensor values, whatever the robot measures from the light sensor has to be multiplied by 1.613 and then 25.808 subtracted from that result before we get a resultant value fit for being used to control our robot. This makes our robot behave better because after doing this, the least value will be transformed from 16 to 0 and the maximum value will be transformed from 78 to 100, which opens up the range. Once we have that, our error value can now be calculated as the midpoint of the two values 0 and 100 can be now calculated as the standard light sensor values minus 50, which opens up the range from negative 50 to positive 50, because now the maximum standard value you can record is 100, and the minimum standard value you can record is a 0. That opens our control from a range of 31 to negative 31. It opens our range from, it opens our control, or gives us more control. We were initially limited between negative 31 and positive 31. Now we have control all the way from negative 50 to a positive 50. That is why it is very needful to do calibration. Calibration can help us in many fields. Assuming you are a medical doctor, you get to a village or you are posted to a remote area, and your thermometer, or you have thermometers that are misbehaving, but you have one thermometer that works properly. What can you do? You record known values, or you record temperatures with the accurate thermometer and plot them against the faulty ones. Then for each faulty thermometer, you can come up with an equation that transforms their faulty values into accurate values. In that sense, you could reuse your faulty thermometers and have them behave properly, provided their behavior is linear. You could employ it in different aspects of life. So wherever you find yourself, let your education count. Apply your principles, apply mathematics, apply science. I hope you have enjoyed this lesson. I'm going to move on to our programming. We will program this, what we have discussed, and come up with our own block to be used in controlling our robot. So we'll build a block that has these formulas in there to standardize the values from the light sensor before we use them in controlling our robot. If you have any questions, leave them as comments. We are more than glad to assist you. We will make sure we answer all your questions. Stay tuned and subscribe to this channel for more videos. Thank you.